So today we're going to finish up on the code review that we started a couple of weeks ago. Now I just want to apologize for not getting to this sooner. It's been a busy couple of weeks, and so now things have settled down and I'm going to have more time hopefully to make more videos. So in the previous video, we went through all the parameters. This is the beginning of the program. We went through all the parameters that you can set to get different effects in the visualization area. And so today what we're going to do is we're going to go through the actual kinematics code, the code that does the kinematics, the motions that you see over here on the right. So hopefully you've seen my previous videos on complex numbers and quaternions, and that you're maybe a little bit more familiar with the idea of matrices. And so matrices are the key to understanding the software that I'm going to show you. Now, the software, of course, I want to make sure that I remind people that this software originally came from Chantal Roth. Okay, I didn't steal it. Somebody accused me of stealing her software. I didn't steal her software. She gave me her software. She converted it from a toolkit called Unity. She converted it to JavaScript, and then I converted it to JavaScript for the P5JS editor. Okay, so I did not steal this code. It was given to me, and I am very, very, very grateful to Chantal Roth for keeping me in the loop in her research and for sharing her software with me. So the main change I made when I got the software from Chantal was I converted her code from using the standard quaternion methods and to using the 4x4 matrices that I have been talking about and promoting on my website. Now, I'm not saying that the 4x4 matrix implementation is better than or more efficient than the standard methods used to implement quaternions, but basically what I am trying to say is that under the hood of the standard implementation of quaternions is the 4x4 matrix. And so basically this is a proof of concept to prove that the 4x4 matrix implementation is identical to, produces the same results as the standard, more algebraic implementation of quaternions. So the matrices that I need for this application are initialized at the beginning here, just to make the coding a little bit easier and cleaner. So, but I also want to point out that there is another kind of a matrix, which is a 1x3 matrix, which we need to define the the y, x, and z axis, okay, the x, y, and z axis, and this is what the matrix looks like for the y-axis. This is the x-axis, and this is the z-axis. So this is like the first entry is the x, the second entry is y, and the third entry is z. And so this will be required, this is the axis. Because we're spinning about the y-axis, we need this matrix here, and because this twist here, let me just show you that quickly. Okay, so the twist is, okay, the twist is actually about the x-axis. So if I set the phase back to 0, actually I set the phase to 90. So when I increase and decrease the winding, which is the twist, you can see it's rotating about the x-axis, which is into and out of the page. Let's kind of look at it this way. So x is into and out of the page, and we are twisting about the x-axis. Okay, so the just so you know, the rotation is happening about the y-axis, which is in this view is up and down, in this view it's into and out of the page. Okay, so we will be using these two axes, these two matrices in the software. So also we have these two parameters, which we're not going to get into in this video, but the extra layers are where I can add extra layers to create a medium, the bulk of the medium, and the vertical shift is the placement of each layer. So I can place, as you can see, I can place each layer, I can place more layers in the visualizer, and so that's what these two parameters are for. Okay, so back to the 4x4 matrices. These are the 4x4 matrices that we need to run the software. The first one I refer to as the location matrix. This is what people would commonly refer to as the vector. Now, this is the only matrix that I am using a 4x4 matrix for, where in reality we could easily use just a 1x4 matrix, okay? But for the sake of argument, I am modeling everything as 4x4 matrices as a proof of concept. And but generally the location would be what you would call a vector, and it would just basically be the top row of the 4x4 matrix. The rest of the matrices need to be 4x4 matrices because they are transformation matrices. So the Q twist matrix is the twist. Okay, that is the twist that I just showed you. So there will be a matrix for the twist. There is a rotation matrix, which is the rotation. Let me just get rid of that. The rotation about the y-axis. And then I need a matrix for the conjugate of that. And then there's going to be a combined matrix, which combines the rotation matrix and the twist matrix. Okay, so there's going to be a combined matrix, and then there's going to be a complex conjugate of the combined matrix to do the final transformation. And there is also a temp matrix, because when we do the multiplications, when we do the complex conjugate, it's convenient to have a temporary matrix, as you will see. Okay, so I'm just gonna quickly go over the setup. I'm gonna actually expand this a little bit so that we can see more of the code and less of the visualizer. Okay, so the setup function, we set up the canvas. We paint the background black. We actually don't need to do that here, so I can get rid of that. Okay, let me save that. Then the color mode is HSB, which allows me to colorize in the way that I want to, based on the distance from original position. Okay, then there's all the user interface stuff, which are the controls. Okay, the controls. That's all set up here. I won't get into that. It's pretty straightforward. And then I have two, these are going to be lists. So I'm going to generate points and put them on the list. Okay. And then I'm going to have the original positions, which would be just the flat plane. So original positions would be without any windings or without any spinning. Let me get rid of those layers. Okay, so the original position would be the location of all these cubes before I apply any of the transformations. Okay, and then the current positions, and actually I spelled current wrong here, so don't get mad at me. That was just a typo, and then once I used it, I had to use it all the way through. So the current position, so I'm going to save a vector, not a vector, a list, which is sometimes called a vector. But I'm going to save a list of original positions and a list of the current positions. So this would be before the transformations, and this would be after the transformations. Okay, and then I have, I decide if I want to do the belt trick. Okay, so if I set up true to do belt trick, it'll do the belt trick. Otherwise, it'll do the hex grid, and we're going to visualize the hex grid today. Okay, then there is the draw function, and actually this is where I set the background to black. I set up my lights. So in the P5JS platform, I can use degree mode. I like degree mode better than radians, especially when I'm teaching, because most people are familiar with degrees. Radians is a little more obscure, and so I'm using degrees. And so when I am setting up, when I'm looking at my phase, so you have the phase down here, so I am displaying using the degrees for my phase. Okay, so this is 0 degrees, and this is 360 degrees, 180 degrees. Okay, so that's why I like degrees. I prefer degrees. I think in degrees in my head much easier than I do radians. Okay, so the orbit control, let me turn this back on. The orbit control, okay, allows me to do this. Okay, the orbit control allows me to manipulate this and visualize it. I can zoom in. I'm using the scroll wheel of my mouse to zoom in and out, and I can rotate and look at this from many angles. So this is what the orbit control does. There's an ortho control here, an ortho command that allows us to do parallel view. It is commented out because it has some problems, and so sometimes I like the parallel view and sometimes I like the perspective view. It depends on what I'm doing. So we're going to stick with the perspective view, and actually in this application, perspective view looks much better. Okay, so then there is the auto increment of the phase. Okay, so that is the phase of the angle, the rotation angle about the y-axis, which increments every time we do every time it calls the draw function. So every time the draw function is called, it increments the phase, and then we update the visualization. Okay, so then we update the medium. Okay, so I'm calling this the medium. This is my medium in my application, and so then we update the medium, and there's an optional draw center object, which we're not going to do today. So what we're going to do is we're going to jump to the update medium. Okay, we're going to drop to the update medium function to show you what's going on in there. And this is basically where we're updating all this visualization stuff. And so in here, there's kind of a lot of stuff going on. Okay, but what I want to, right, so we're calculating some distances so I know how far away each object is from the center, and I'm also calculating the difference between the original position and the current position or the new position, and yeah, using that to colorize this this region here, right? So, but today the most important part of all of that's going on is a function which I call do kinematics. Okay, I'm going to just sort of focus on that right now. Okay, so let me save that. So the do kinematics, I pass in the phase, I pass in the y-axis for the rotation, I pass in the x-axis for the twist, and then I pass in the original position. So for each position on the screen, or sorry, for each object in the model, I'm calling do kinematics. So here I say for I equals 0, I is less than the number of original positions. This actually equates to the number of original positions, the number of objects in my model. I am going to do the kinematics. So this is where the guts of everything is. Okay, so we're going to have a look at the function, which I refer to as do kinematics. So you can see here's my do kinematics function, and here is the phase. This is axis 1, which is the y-axis, axis 2 is the x-axis, and x, y, and z are the coordinates of the original point. Okay, so the first thing I do is I set up the rotation matrix. Okay, this is the rotation matrix that uses the phase. Okay, so I have a function that sets up the matrix, so I don't have to like put the matrix here. Set up Q matrix sets up the 4x4 matrix, and so what I do is I pass in the parameters for the matrix, and then the setup Q matrix places the entries into the 4x4 matrix into the correct location. Okay, so and maybe we'll just have a quick look at that. Where are you? Okay, so here is my setup Q matrix. I'm only going to do this once. I'm going to be using this over and over and over again. Okay, and I'm going to move this over a little bit so you can see it better. So here you can see I've got W, X, Y, Z, and the matrix that we're going to put it into. So this is a pointer to the matrix that we're going to be setting up. And so you can see the W's on the forward diagonal, the X's go here, the Y's go here, and the Z's go here. And this controls the sense of the parameters. So let's just say, for example, if X is positive, then this will be positive and this will be negative. But if X is negative, this will be negative and this will be positive. Okay, so this makes sure that the matrix gets set up in such a way that all of the sense of all of the inputs of all the matrix entries are correct. So now that we know how the matrix is set up, we're going to go into back to the do kinematics. And so the first thing we do is we set up the rotation matrix. Okay, in order to do that, the first thing we need to do is we need to plug in phase divided by 2, because the rotation is going to happen in 2 parts. As you've seen if you've watched my previous videos on quaternions, you would see that the quaternions rotations need to be done in 2 parts. You need the rotation and you need the conjugate. So here I'm setting up the rotation and the conjugate matrices, and they need to be, you need to pass in the phase divided by 2, because this is going to do the first half of the rotation and this is going to do the second half of the rotation. Okay, and so you also have to multiply each component of the x, y, z. Okay, so this would be w, x. So I'm going to move this over a bit so you can see it better. Okay, so we've got the forward diagonal is the w in the matrix setup, and that is on the forward diagonal. And then you have the I, J, and the K components of the matrix, which are in various locations of the matrix, which gets set up for you automatically in the setup Q matrix function. And so you have to multiply the x, y, and the z, the I, J, and the K by the x, y, and the z of the axis that I showed you earlier. And so because this is the y-axis, this is going to be 0. So this component is going to be 0. This is 1 in the y-axis, so this is going to be not be 0, and then the z is 0, so this one is going to be 0. Okay, so but they don't have to be 0, but just because of the way we set up the axis, because 0, 1, 0 is the y-axis, that this component is going to end up being 0. This component is going to end up being 0, and this component is going to not be 0, and this is going to allow us to rotate about the y-axis. Okay, so to set up the conjugate, you do exactly the same thing, only you negate the I, J, and K components. Okay, and that's all it is. So that's how you set up the rotation and the conjugate matrix to do this rotation here. Okay, so next we're going to set up the twist matrix. Now, Chantal refers to this as the kernel matrix, and she got this terminology from a man named John Close, who she's working very closely with, yes, pun intended. 2 really smart people working together on this, and I am really lucky and grateful to be maybe a fly on the wall and to have access to the code that they developed together, as it is really going to help me out in the research that I am doing as well. Okay, so in order to set up the twist matrix, we need a little bit more information than we do with the rotation matrix. With the rotation matrix, basically, I only really need to know the phase. Okay, I need to know the axis and the phase. And but for the twist, basically how that works is the twist. Now what I'm going to do is I'm going to just stop this. Okay, I'm going to stop this. And then as you can see, the twist angle becomes less and less and less and less and less as you go further away from the center. So the twist angle is really, that I am setting up here, is really the maximum twist angle. So the maximum twist angle is at the center, at the origin of my medium. And then as you go further and further and further and further away from the center, the twist angle is less and less and less and less and less. Okay, so that's kind of how that works. And so we need to, first of all, we need to calculate the distance from the origin. Okay, so we use the original position. We do it the standard way that you do to calculate the distance. Okay, and then we calculate a sort of a fraction. This is a fraction of the twist that we want to multiply with the maximum twist angle to get the twist angle depending on which object this happens to be. Okay, so we need to calculate the twist rotation angle before we can set up the twist quaternion. Okay, so here we have, let me move this over again so you can see it more clearly. Okay, so here we have almost exactly the same as for setting up the rotation, only we're setting up the twist quaternion using the same setup Q matrix. And so we take this twist angle and divide it by 2 like we did before, and then we've got the axis 2, which is the x-axis, and as I showed you, the twist is happening, let me just see here. Okay, so the twist is happening about the x-axis, okay? And so we set up the quaternion just exactly like we did before, only we don't need the conjugate for the twist quaternion. And the reason for this is because the twist quaternion is going to be operated on. So instead of it being an operator, it's going to be operated on. And so here I just have like a quick little simplification of what we're going to do right here. So basically we're going to multiply the rotation matrix by the by k. Here k is actually the kernel or the twist quaternion, and so we're going to, so the kernel, the twist quaternion is going to be, is between, sandwiched between the rotation matrix and the conjugate rotation matrix. And that's why we don't need the conjugate for this, because it is actually being operated on. It is not the operator, it is the operatee. Okay, and so what we do now is we're going to be generating a combined matrix. So we're going to combine the rotation matrix with the twist matrix, the rotation quaternion with the twist quaternion. And so what we do is we take the rotation quaternion, multiply it by the twist quaternion, and store it in that temporary quaternion. And then we multiply the temporary quaternion by the conjugate quaternion to get the combined matrix. So now we have a combined matrix of the twist and the rotation matrices. And so then we're going to generate the conjugate of the combined. Okay, so we're going to take the combined and negate the I, J, and K components to get the conjugate combined matrix. Okay, and this, the combined and the conjugate combined are what we're going to use to transform the objects, okay, to change the location, to calculate location of the object and to calculate the orientation of the object. So as you can see, these objects, not only are they moving, but they are reorienting themselves as they move, okay? And so these two matrices are going to be used for both the translation and the reorientation of these cubes. Okay, so the next thing we do in this function is we are going to do, I'm going to move this over a bit so you can see it better. We are going to do the transformation. Okay, we're going to take the original location. So now what I'm going to do is I'm setting up a new matrix. It's the location matrix. Okay, and this is the one that I said it's kind of overkill to use a 4x4 matrix. I could easily just use a 1x4 matrix to represent the location and to do the multiplication, but just for the sake of simplicity, so I can use the same multiply matrix function for everything, basically that's why I am doing it this way. So it's not the most efficient way, but it is the actually simpler in terms of implementation. So in the case of the setting up the Q matrix for the location, which most people would refer to as the vector, I just call it location because it is a location in 3D space of these objects. In order to set this up, we need to pass in the W, X, Y, and Z. And in this case, for the location, the scalar is not that important. Most people set it to 0, so they say W equals 0. But it turns out I discovered and realized working with the software that it actually didn't matter what you set that to. It doesn't change anything whatsoever. So I put in 666 just for fun. And it doesn't matter. I could set this to 10,000 and we'll run this, you'll see it doesn't make any difference whatsoever. Okay, so that the scalar is ignored when you're doing rotations about some axis and you are setting up the quaternion for the location. The scalar can be anything, it's ignored, it doesn't really matter. Okay, so I can set that to whatever I want. I'm going to put it back to, I'm going to go 222 because I like 222, and we'll run that, and you'll see that there is no difference whatsoever. Okay, so so you set up the Q matrix, you set up the quaternion matrix using the setup Q matrix, and then we do the multiplication. We do basically we take the combined and we multiply it by the location, okay, and store that in temp, and then we take the temp and we multiply that by the combined, and we end up with the new location. So this is now the new location. Okay, and then what we do is we turn that location into a new position. So that is now the new position. And in P5JS there is a create vector, and P5JS they refer to a location as a vector. It's very common to do that in computer science. I'm trying to avoid the word vector altogether just for the sake of argument. You can call it a vector or not a vector. I refer to it as a location. Okay, so you set up the new location, and the new location is stored in the top row because I'm using row convention. That's another important point in my code. I'm using row convention. So the top row of the matrix contains the answer, the new location, and so 0, 1, 0, 2, and 0, 3. Because 0, 0 is the new scalar, which is going to end up being exactly the same as the original scalar, and I'm not using that to do the rotation, so that is ignored. And so I take the new location and I create a new position. And that new position is the new location that this cube is going to be in 3D space. Okay, and so so that's half the battle. Okay, that's 90% of the battle actually. The next thing we need to do is we need to reorient the cubes. Okay, as you can see, the cubes are reorienting as they go around the wave, as the wave goes around in a circle. And so I need to calculate the orientation of the cube and then apply that to the object in this visualizer. So to do that, I developed a function called extract Euler angles. Okay, and so what this does, so what I do is I pass in the row vector from the combined matrix that we generated. So the row vector is basically the top row, and again I want to emphasize that I am using row convention, and a lot of people use column convention, but I'm using row convention, so I pass in the row of the combined matrix, the combined quaternion matrix. And so let's have a look at that. Okay, so this function, basically what it does is it uses a bit of trig and the w, x, y, z parameters from the combined matrix to extract, to calculate the roll, pitch, and yaw of these objects that we want to apply to these objects. And so not only are these objects changing their position from the original position, they're also changing their orientation as the wave orbits in a circle as we see here. And so that is the purpose of the extract Euler angles. Okay, I pass in the row vector of the combined quaternion matrix and I get out the roll, pitch, and yaw, which I return. So this function, the do kinematics function, returns the new position, the x, y, and z new position, and the roll, pitch, and yaw that we just calculated right here. So that's pretty much it. This is the hard work that the do kinematics function does. Okay, so in the update, where are we here? In the update medium function, we call the do kinematics, and then we return the result, which contains the new point, the new position, and the roll, pitch, and yaw parameters, and then we apply them to these objects, okay? And so the rest is just the drawing of the, so first we translate to the new position, and then we apply the roll, the yaw, pitch, and roll in this order to the individual objects, okay? And then we draw the object. In this case, I'm drawing these boxes because the boxes show the changing of the orientation better than the spheres would, okay? So if these were spheres, it would be very difficult to see that these objects are actually changing orientation as well as changing their location. Okay, so that's pretty much it for the code. I am going to leave the link to this code in the description as I did before, and you can have a look at it yourself and play around with it. And of course, if you have any questions, you can feel free to ask me. Okay, otherwise, I hope you're having a good day, and I am going to go and hopefully continue my research into creating the medium for the propagation of light, which is the whole point of this research, is to try and develop a model that could act as the medium for the propagation of light. And it's not just the medium for the propagation of light, it's also the medium that supports magnetic fields and electric fields. And so this medium has to do, and also propagate light. So this medium has to do a lot of things. And so that is the goal of my research. And I know this is the goal of Chantal Roth's research as well, and her colleague Robert Close, who unfortunately earlier I referred to as John Close. I apologize for that. Robert Close is doing some really good work. John Macken is doing some really good work. And so I'm just lucky to be a fly on the wall of all these great minds, these great thinkers, and that aren't afraid to admit that there might be an ether, that there could be an ether, that there must be an ether. And so I think we still have a lot more work to do, but I think this is a good start. And I'm going to continue my research throughout the winter, and I will keep you posted when I come up with something, when we as a team discover anything new. And so I'm done for the day, and so I will be back.